in that sort of sense. Then, for example, if you guys have done the smell lab yet, you may have noticed that there are certain examples of molecules that you can smell that have different chirality. The smell of wintergreen is very similar to the smell you get from caraway seeds. And most people can differentiate these two smells only by the tiny difference in their chirality, being left-handed or right-handed. There's some people that actually can't differentiate this because, for some reason or another, one of the enzymes that's been encoded in their genetic material actually doesn't have the proper handedness. I guess, for example, if I can get somebody to volunteer real quick, I need to borrow somebody's hand. All right, so give me your right hand. Am I getting a video with this? Here we go. All right, so if you have your right hand, I use my right hand. It works. We can shake hands. Now, still with your right hand, it doesn't work very well. So I can only really get a handshake to work if I have a right hand. If I can get, I certainly do another volunteer. Now, for example, let's say that I've got a hand that is not chiral. For example, a glove. A glove, the palm or the back of the hand, there's no difference. It's all just, maybe it's even latex. It's some kind of glove material. It's all white. I can't tell the front from the back. I don't know if it's the right hand or left hand, so I can shake it with my right hand just as well as I can shake it with my left hand. I can't tell the difference. You know, oh, that's entertaining. So, again, you might see that, these are also mirror images of each other, but I can rotate it together, and they do line up perfectly. So these hands are not chiral, unlike the hands of most humans. This continues on. If you couldn't quite see the video, here's a set of non-superimposable mirror images, just like we had before. Look at that. They don't superimpose. They're the wrong colors. Hopefully nobody happens to be yellow-red colorblind. That would be another set of coincidences. In nature, there's also chirality everywhere. In our amino acids, they all have the choice of being left-handed or right-handed amino acids. Left we call L, we have levorotary and dextrorotary compounds. Levo meaning left, dextro meaning right. This is in regard to the way that they rotate polarized light. If we shine light on these, we can actually separate them out based on whether it's left-handed or right-handed because of the way that light will actually rotate on its own. The interesting thing about this, however, is that our bodies are composed entirely of L amino acids. D amino acids can be produced, they can be available, but our bodies will only use L. The same goes for, as far as I can tell, all biology on our planet. If you had D amino acids, we could eat these, and they can be produced. We can even get some amount of energy out of them. We can get some sort of caloric energy. We can get energy from it. But we actually can't build new materials out of a D amino acid. We can't build muscle. We can't build proteins. We can't do anything with the raw materials. We can only use L. The same way, we can only produce right-handed DNA. We aren't able to produce left-handed DNA. It's a different kind of helix. It's a different handedness. We're only able to actually produce the one. Interestingly enough, despite the fact that we use basically left-handed amino acids, we use only right-handed sugars. So we use right-handed sugars, left-handed amino acids, and we get right-handed helices. This is a fantastically strange thing that people are constantly arguing about how it is that we have this homochiral chembiogenesis, to use the fancy Greekish words. It's unclear as to exactly why these sort of things happen. If you want to see a picture of how right and left-handed works, imagine my hydrogen is always pointing the direction of my thumb. So I can have a right-handed or a left-handed version of an amino acid, where R identifies what kind of amino acid it is. And actually, in between the morning lecture and the afternoon lecture today, the following paper was published in Council of Chemical Research on the origin of single chirality in amino acids and sugars in biogenesis. So when I tell you that we are still trying to figure out how this works, believe me, I promise this paper was actually truly first available today. This is a constant that's going on. We're trying to figure out more and more about how this works, because it's bizarre at some level. The fact that we have the choice to have right-handed or left-handed amino acids and sugars, but we only use one. It's unclear as to why this choice would happen. People have different theories about the possibility of polarized light being available in the early universe, or some kind of new kind of physics that's going to lead to a certain chirality, but all these things are unclear. What we do know is that chirality is immensely important. The same way that I can't shake a left hand using my right hand, that means that something in my body, a protein, an enzyme, can't work with the wrong-handed substituent. So if I have the wrong kind of an enzyme, the wrong kind of another protein, the wrong kind of another chemical in my body, my enzymes are unable to interact with it, because they have a handedness, and they can only shake the right kind of hand. So, now that I've talked for a while about chirality, let's take a look at octane, and which one of these can possibly be chiral. So just real quick, we'll try to see what you guys think. Here we go. Think about what it means to be chiral. How can we have a mirror image, and how is it possible that we are able to superimpose with it or not? This is the real question, to see if the number of people who respond is greater or less than when I started out. If I scare people away or not. We're close. Woo! All right, we've actually gained 2 people. All right, I call this an improvement. So, what do we think? Which one is chiral? We are not sure which one is chiral. We have a slight preference for B, but A and C are still pretty good contenders. All right, if I can get the video again to take a look at the mirror. Let's see. All right, so we notice that in this case we have this molecule can be chiral, because if we look at its mirror image, we know that it can't be superimposed. When we look at this molecule, we also notice that it has a tetrahedral type geometry. So that's direct number 4, forms 4 bonds. It forms 4 bonds to 4 different things. For example, if the pink and green were for some reason the same color, then we would have this working out, and then the problem is that pink and green are different. So for example, if I take a look at these molecules, I can show that they are mirror images. See that mirror image of that one? Looks quite a lot like mirror image of this. But I actually can line them up. These are mirror images that are also superimposable. It's because I only have 3 different kinds of things. One of them is repeated, so as a result I can get them to line up perfectly. So the problem only arises when I have 4 different substituents onto one 4-coordinated tetrahedral spot. So that said, let's take a look at this question again and consider which one of these is likely to be chiral, which one is going to have 4 different things attached to a certain tetrahedral center. All right, in the next 20 seconds, see if we can get this above 452. Please make me feel good about myself. Come on. Getting close. 6 seconds, 5 seconds. Go, some students. All right, we'll be the last students, 2 students in between those two. Let's see what we're looking at now. All right, looks like B is now the new favorite. And, in fact, I agree. B it is. So, if I move over, you can see that B is the only situation in which I can actually draw that I have 4 different substituents around one of the carbons. In the case of A, around, say, this carbon, I have a hydrogen, then I have 2 identical CH3s, then I have this other guy around here. Here I've got 3 identical substituents. Here I've got 2 that are identical. Here I have 2 that are identical. In any other case, I've got 2 hydrogens here and here, 3 around here. So B is the only situation where I actually have a carbon that has 4 different things around it, which is why it is the only one of those that is chiral. Another question, while we're at it. This is a sneaky little question. So let's say that I have 2 chiral isomers. They're left or right-handed, and which of the pairs must necessarily be chiral? Is it where I have 2 right-handed molecules, 2 left-handed molecules, or a mixture of the 2? Let's see what we like. Maybe another 15 seconds. Get the rest of the people to answer, maybe. Getting close. Almost all right. So let's see what we're thinking. Will it let me show? All right, looks like most people are answering that they think that the answer is C, a combination of left-handed and right-handed molecules. If we look at the picture we have on the right side of this page, I have a left hand, I have a right hand. I have the 2 different chiral possibilities, and they form molecules like this. This is not a chiral molecule. Part of the way we can easily define whether or not something is able to be chiral is that we can, if it's possible to draw a line, define a plane through the middle of an object. Say, for example, one of these gloves, if I draw a line and have a whole plane going through the middle of this glove, both sides of it are mirror images of each other. However, if I take my hand and I draw a line right in the middle of it, the sides are different. The one is the back of my hand, the other is the palm of my hand. There's going to be a fundamental difference between the 2 of them. Similarly, if I draw a line through the middle of this, if I put half of it into this mirror or something like that, I can't actually do that, but imagine that I could, then the 2 sides are going to look different. However, if I take one of these guys and define this plane, this line through the middle, the 2 halves of this green one are going to line up, the 2 halves of this brown are going to line up, and then these 2 white ones on either side will line up on that mirror image. Similarly, in the case of where we have D and L together, I can draw a line, I can envision a plane that would actually map these 2 things onto each other, 2 halves. So I will tell you right now that based on the picture that it shows us, the answer C, DL, is not chiral. So that means that C is incorrect. So let's try this one again. Talk people around you and figure out if you think that A or B is the answer, given that C is not. Running a little bit short on time. I'm going to speed this one up. Don't worry, I'm not actually going to click on this one in a way that will allow it to be worth points. So do you think it is A? Do you think it's B? It's like A won out. People still voted for D and E also, I guess. A little bit of C. What we will actually find is, in fact, both A and B are possible answers. Thank you, Professor Nietzsche. All right, so it's also worth noting, I think, that we can have chirality, we can have handedness, and a couple other examples. We have 3 minutes left. I'm going to randomly talk about chirality for a couple minutes. Just you try and stop me. So, for example, on top of chemistry, chemistry has to do with the way that we organize things. It's the way that we connect things together. This can be related to a part of mathematics called topology. For example, I can draw a pretty little thing like this. We call it a kind of a knot, which is why it kind of looks like a knot. It's called a trefoil knot. And as a result of having similar mathematics as the connectivities between different molecules can have, we can actually have a right-handed and a left-handed version of a knot. We can also talk about the example of spin. Spin is, in fact, a consequence, to some extent, of helicity. I'm not going to talk about this one too much, but basically just believe me when I say that spin up and spin down are not only related to some imaginary magical thing that I made up, it is, in fact, actually related to Chirality has to do with the ability of the universe to have things that are right or left-handed in an additional way rather than just organization in the conventional three spatial dimensions. All right, now you can leave. If you have any additional questions, I can stand up here for a couple of minutes since there's going to be no office hour with the professor actually being gone.